Hi and welcome again to these videos on structural dynamics. Today the topic of the video is response spectra. So response spectra are used in paraseismic calculations of buildings and especially in the Eurocode 8. So first of all we need to define what are response spectra and the different types of response spectra.
So in order to understand response spectra, we need to go back to the equations of motion of a 1 degree of freedom system excited by the base. I remind you that we make a change of variable to write the displacement in terms of relative displacement with respect to the basis, and we end up to the equation of motion of a 1 degree of freedom system with an excitation given by minus m times the acceleration of the base. This corresponds to the earthquake base acceleration, and if we want to compute the response in the time domain, we can do a convolution of this force minus mx dot 0 with the impulse response, which for 1 degree of freedom system takes this expression, so that we can solve for the relative displacement of the mass with the following integral. If we do this, for example, with the Santa Cruz earthquake, and we take a system that has a natural frequency of 6 Hz and a damping of 1%, this results in the response of the mass to the earthquake. We can compute this convolution integral for different values of the natural frequency of the 1-DOF system. So this is, for example, when the natural frequency is 0.5 Hz and the damping is 1%, we get a maximum of about 0.1 meter of relative displacement. In the case that the natural frequency is 1 Hz, it goes up to 0.2 meters, and in the case that we have 2 Hz, it is again around 0.1 meter. So one value in a response spectrum corresponds to this maximum of the absolute value of the amplitude of the relative displacement of a 1-DOF system with a given natural frequency and damping coefficient. So you build a response spectrum by varying the natural frequency of the 1 degree of freedom system and then taking the associated period, t is 1 over f, for the x-axis. So this is the result for the Santa Cruz earthquake and a damping of 0.01%. You see that the x-axis does not correspond to the frequency of excitation. It is always the same excitation by the earthquake. It corresponds to the eigenperiod of the 1 degree of freedom system that you consider in the computation. This natural frequency of the system corresponds to f equal 1 over t. So for example, here when t is 2 seconds, you see that it corresponds to the natural frequency of 0.5 Hz. When it is 0.5 seconds, it corresponds to 2 Hz. And note again that this response spectrum is specific to an earthquake. Now, we talked about the relative displacement spectrum called SU. We can also work with the relative velocity spectrum if we consider now the relative velocity instead of displacement. And we can also define the absolute acceleration spectrum where we look at the maximum of the absolute acceleration, so acceleration of the basis plus relative acceleration. We also define two other types of spectra. The pseudo-velocity spectrum is obtained by multiplying the displacement, the relative displacement spectrum by the natural frequency omega n, and the pseudo-acceleration spectrum by multiplying SU by omega n squared.
Response spectra are used in numerous codes and norms. And in Europe, these response spectra are defined in Eurocode 8 related to dynamic responses of structures to earthquake excitation. So let's see how Eurocode 8 defines these response spectra for paraseismic computations.
Now, if we look at an undamped 1-DOF system, these are the equations of motion for base excitation, and if you divide by m, you obtain the following equation, so that the total acceleration xr dot dot plus x0 dot dot is equal to minus omega n square times the relative displacement. Therefore, the pseudo-acceleration spectrum, which is defined as omega n squared times the relative displacement spectrum, is should be close to the total acceleration spectrum SA. And this omega n squared SU is called SE in the Eurocode. It's called the elastic response spectrum. It is therefore an approximation of the total acceleration of the structure, which is valid when the damping is small. So here we compare for the Santa Cruz earthquake the total acceleration spectrum SA and the pseudo acceleration spectra, which are defined here, and you see that they match very well, at least for low values of the period where the frequency, where the value of the spectrum is high. Now, if you change the value of damping for this acceleration spectrum, you see clearly that as you go from 1 to 3 and 5%, the maximum of the response spectra clearly decreases. In the Eurocode, the horizontal elastic spectrum SE is defined by a simplified curve, so representing the trend of the spectra that we saw before. I remind you that SE is omega squared n SU, and this is the general shape of SE. And so it has 4 parts. From 0 to TB it is a straight line, increasing line. Then it is a plateau between TB and TC. Then it decreases in between TC and TD and has a different trend after TD. So in this equation there is AG, which is the ground acceleration, S is a soil factor, so depending on type of soil, and eta is a damping correction factor, which is equal to 1 for 5% damping. In the Eurocode A there are 2 types of soils, and so for type 1 you see that depending on the ground type, which is labeled A, B, C, D or E, the values of S, TB, TC and TD are different. There is a second type, which is the one used for Belgium, where the values are given also as a function of the ground type, and this is a comparison of the response spectrum for these type 2 grounds. Now, SE is the elastic spectrum, but in order to compute the response of the structure under seismic excitation, you need to take into account the possible inelastic behavior of the structure, taking into account a behavior factor Q, and you add a lower bound factor beta. So the resulting expression of SDs are given here, and this is a comparison of an elastic spectrum with a design spectrum where Q is equal to 1.5. So the effect is to reduce the spectrum of response by taking into account the inelastic behavior, and this is called the design spectrum, which is used for the calculations.
As we saw, response spectra are specific to certain types of earthquakes, and they are also related to the response of a single degree of freedom system with a specific natural frequency. But how do we do when the structure is a multiple degree of freedom system? Well, as we will see, the basic idea is pretty straightforward. We know that this multiple degree of freedom system can be separated in independent 1 degree of freedom systems by projecting in the modal basis.
For multiple degree of freedom system, we can project the equations of motion in the modal basis, and you see that it results to an equation which is similar to the one for a 1 degree of freedom system, but there is an amplification factor, gamma I over mu I here at the denominator, which means that if you are looking at the response spectrum, first you can determine what is the maximum amplitude, but in terms of modal displacement, by solving this equation.
and you have to use then the amplification factor. So the maximum will be given by SU, so the displacement, the relative displacement spectrum, and you just take into account the amplification factor to get Zi max. Now, once you have the maximum Zi, you can look at the maximum displacement by expanding, multiplying by the given mode shape, and you will have the contribution of mode I to the total displacement vector on all degrees of freedom. You can do the same for the acceleration by considering now the pseudo acceleration, the amplification factor, and multiplying by the mode shape. Once you have done that, you need to combine all contributions for all modes. And there is one method called absolute sum method. So you just, for one quantity r, whether it is a displacement or an acceleration or a force, you compute R max as the sum of the absolute values of all values of Ri, of all contribution of the modes. This usually leads to an overestimation, so that the most established method to do that is the square root of sum of squares, also called SRSS method, where R max is given by the square root of the sum of Ri squared. Let's take an example of a two-floor building where the stiffnesses of the columns are replaced by an equivalent stiffness 2K for the first level and K for the second level. The first level has the mass 2m and the top level has the mass m. So this is the equivalent system which is excited by the ground. Here we take these specific values for K, m, and a damping of Xi is equal to 5%. So for this system, this is the stiffness matrix, this is the mass matrix, from which we can compute natural frequencies and mode shapes. And by looking at the values of the natural frequencies in radians per second, we can extract the period, which in this case is 1 second and 0.5 seconds for the second mode. Now we can look at the elastic spectrum at these two values of t. And so we are looking at SE at T1 and SE at T2. So this is how mode 1 will respond. This is the value of acceleration, modal acceleration for mode 1 here, and this is the value of modal acceleration for mode 2. Now we have to take into account the Q factor, which divides by 1.5 this value of acceleration. We have to compute the modal participation factor, so by how much is each mode excited, and this gives us for gamma 1 over mu I, so mu 1, so for the first mode it gets 4/3, and for the second mode we get minus 1/3. Now to get the maximum modal displacement, considering an acceleration of the ground of 1 meter per second square, we have to multiply SD at T1 by AG, the acceleration of the ground, and the amplification factor, and divide by omega 1 squared to go from accelerations to displacements. We do the same for the second mode, but be careful because these are only modal amplitudes. So to have the displacement at the top of the building, we need to multiply this maximum value for mode 1 by mode 1, and the maximum value for mode 2 by mode 2. Now we're going to look at top floor displacement, so this is the second degree of freedom, and we need therefore to combine these two values. We use the SRSS method, and it results in a displacement at the top of 1.42 centimeters. We can also evaluate the shear force at the bottom of the ground level columns. So the shear force is given by 2K times the relative displacement between the ground and the first level. So this is given by Z max, so the modal amplitude of displacement, times the mode at level 1. So this is the relative displacement of level 1. By doing that, we find for mode 1 2.77 kilonewtons, and for mode 2 we get 682 newtons. By combining these two values
With the SRSS method, we get a value of 2.859 kilonewtons for the shear force in the columns at the bottom.
So nowadays, even in regions where there is very low seismic activity, it is often required to check the building's response for earthquakes. And we have discussed here the calculation principles that are in Eurocode 8, which are based on response spectra. The response spectra are defined for 1 degree of freedom system, but the basic principle that we have discussed before, which consists in computing the natural frequencies and the mode shapes of the structure beforehand, allow us to treat this as a combination of single degree of freedom system, and then to be able to assess either displacements, accelerations, or resulting forces in buildings which are excited by earthquakes.